class, we are going to learn something very, very interesting, that is differentiation. It's a new chapter and it's going to be very interesting. So let's move on without much delay. So before we move on into the concept, let's understand what is differentiation. So here we are going to deal with functions. If anyone is unaware of what is a function, please do visit the chapter videos of limits and continuity and then move on with this chapter. So let's take an example of a function. Y is equal to x square plus 2. So this is a function. In general, a function can be written as f of x. Y is equal to f of x is a general representation of a function. It means that y is given in terms of x and it's a function of x. Okay. So what is differentiation? When we make very small changes to the values of x. From this, it is very clear that x is an independent variable where you can decide the values that x can take. So that the domain of this function is basically determined by the values of x. So x is an independent variable and the values of y are dependent on x. So whatever values you give to x, the values of y will change accordingly. For example, if I give x is equal to 1 here, my y will take a value of 1 square plus 2, right? X is 1. I replace 1 in place of x and try to find the value of y. So my y will be 3. Now, if in case I give a value of x is equal to 2, my y will be 2 square plus 2, that is 4 plus 2, that is 6. So depending on the values of x, there's a change in the values of y. So this is what we are going to learn in this chapter. The rate of change of a variable, that is the dependent variable, with respect to the change in the independent variable is basically called as differentiation. To explain it to you in detail, let's look into this table. So let's consider y is equal to x square. Now, if I give value of 5 to x, my y becomes 5 square, that is 25. Now, let me just increase x by a very, very small quantity. A very small increase to x. That is, I'm increasing it by 0.1. So, add 0.1 to 5 and I make it 5.1. Now what happens to my y? My y will be equal to 5.1 the whole square. So that's nothing but 26.01. So y is increased by 1.01. So the increase in x, let's denote by delta x. My delta x is the increment or the value with which we are increasing the value of x. So what did I do? I added 0.1 to my original value of x. So that is my increment. I denote it by delta x. So what happens to my y? It increases by 1.01. From 25, the new value is 26.01. That's nothing but 1.01 of increment, right? Now let me do a bit of change. I'm making it 5.01. So to my original value, I'm just adding 0.01 and not 0.1. So the increment is even more minute, even more smaller. So what happens to my y? My y value becomes 25.1001. You can try squaring it and observe what happens to y. So my y is basically 5.01 the whole square. So that's nothing but 25.1001. I'm sure that you all know how to square decimal numbers. Now, so what happens to my y? My y is increased by 0.1001. From 25, it has gone up to 25.1001. We are basically comparing it with the base value of 25. Now, we'll move on. Now, I'm even more reducing the change. It's just 0.001 of the increment. So, what happens? It's 25.01001. So, the increment is 0.01001. It's even more smaller. Now, let's reduce the increment even smaller than that. 0.0001 will be my increment for x. So, what happens to my y? The y gets increased by this value. So, what do I understand from this? I keep reducing my increment from 0.1 that I increased. I made it 0.01. Then I made it 0.001. Then I made it even smaller, 0.00001. So, I keep reducing. So, how do I represent that? In mathematical terms, I can say that delta x is very, very small. It is almost 0. It's a very small increment that I'm giving, meaning it's almost negligible. So, it's delta x as it tends to 0. My increase in y is also going very small. Look at this. It was 1.01, more than 1 initially. Then it became 0.1001. Then it became 0.01001. I'm sure you all know how to compare the decimals. And you are able to see that the numbers, the increment of y is also becoming very, very, very small. Right? So, my delta y is also approaching 0. Okay, so basically we are changing the values of x and looking at its impact on the values of y. So when I increase a very small quantity, it does make a change in y, but that change is also negligible. Now, let's look into the ratio of this. Ratio of increase of y and increase in x. So when you observe the ratio, delta y by delta x. So what happens? I basically have to divide both the quantities and see the ratio. So delta y by delta x here is going to be 1.01 by 0.1. How do I find this value? It might look complicated now. So it's better that we shift the decimals and try to eliminate the decimal in the denominator and the numerator so that it becomes easier for us to evaluate. So I'm planning to shift the decimal to 2 places and throw it out. So similarly, I can't do anything only to the numerator. I'm going to do the same thing to the denominator also. So let me shift this to 2 decimal places. I have only one number, so I'll add a 0. So after the decimal point, towards the end, how many ever zeros you're going to add, it's not going to affect the value, right? So this gets converted into 101 by 10. So this is nothing but 10.1. This is my first ratio. So the same way I'm going to find the ratio here, del y by del x. I get 10.01, 10.001, 10.0001. So almost everything is leading to 10. So I can observe that my ratio, if I make a very minute change to x, it affects the y, and the ratio of the change in y with respect to x is going to be almost 10. Right? So this is called as differentiation. The rate of change of y with respect to x. Since we're dealing with ratios, I'm sure you all know that ratios can never be negative. It does not carry any number, right? So now, whatever, whether it's an increment or a decrement, this particular ratio is called as the derivative of x. Now, this del x is very, very small. So basically, limit del x almost tending to almost 0. This is called as our derivative. So how do I express that? Instead of putting the del here, I'm going to change it to d. So derivative can be expressed as d, which gives us a better convenience to work. So we have limit del x tends to 0, just to denote that the increment in x is very, very, very small, almost equal to 0. The ratio of del y and del x is called as your dy by dx. So this is your derivative. So how do we call that? You can also name it as d by dx of y, or you can call it as d by dx of, y can be represented as f of x. So this is basically the differentiation. Interesting, isn't it? So we'll start solving problems and then you will understand better, I'm sure. So now we saw what is differentiation, right? So what are our observations from the table? We'll quickly summarize before we solve problems. So we make the following observations from the table that we had already seen. Del y varies when del x varies, right? So when we varied the values of x, there was a sea change in the values of y, correct? So del y varies as del x varies, because it's a relation between x and y. Now, we also saw that as del x tends to 0, when del x was a minute change, of course, del y was also tending to 0, right? So, but the ratio led us to the value of 10. These are the observations. You can pause the video here and take it down for your better understanding. So this example, it led us to the fact that del y tends to 0 when del x tends to 0, but the ratio was tending to a finite number. It necessarily need not be 0. It leads you to a number that's finite. It could be 0 sometimes, but not always, right? So the limit, and then the limit del x tends to 0, del y by del x is equivalently represented, right? It is represented by dy by dx, and this is called as the derivative of y with respect to x, and is read as differential coefficient of y with respect to x. So now, why are we learning all this? In life, any two quantities are always related, and both are variable quantities. So when there is a change in one, there's obviously a change in the other. So let's suppose you're driving on the road. The time keeps changing. That's a variable quantity. And then your speed also changes, right? You cannot be driving with the same speed, right? So obviously your distance also is changing. So one quantity is changing with respect to another. So the change in distance with respect to time is called as velocity. It's a very, very small example that I'm telling you. So in everyday life, there are changes in the cost of an article, the number of articles that you buy, the vegetables you buy, the quantity that you buy. So depending on the increase or decrease in rate, the amount of quantity also differs, and it has an effect on each other. So this has an everyday application and a very, very important concept in mathematics, and a very, very interesting one. So let's move. Okay. So every time I cannot be giving an increment and trying to find the change in the other variable, right? It's a complicated procedure. So what do? We derive at formulas to make it easy for us to apply for every sort of function that we are dealing with. So let's do that now. We'll find a generalized formula so that we can apply and find the derivatives of even complex functions. Okay. So let's take an example of a function. Y is equal to f of x. So this is my function, my y in terms of x. Okay, I'm going to increase the value of x by a very small quantity. So what do? I do x plus del x. This is my increase in the x value. Now, this increase impacts the y value. So y is also increased by a negligible value, y plus del y. So how do I express my new value of y? I write y plus del y is equal to f of x plus del x. Now what is my derivative of y with respect to x? Limit del x tends to 0, del y by del x. This is my dy by dx. Now what is this del y? Del y is the increase in the value of y. How do I get that? Let me name this as 1 and let me name this as 2. What is my increase in y value? That is nothing but the difference of this and this, right? So I have f of x plus del x minus f of x. This is my increase in the value. That is, from this I am reducing this. So I end up in the increase. From the new value and taking away the old value to get the increase in y by my del x. That is the increase in x. From the new value, that is x plus del x, I reduce my original value to get the increase in x. So this x is again negligible. So this is my dy by dx. So what do? I can cancel x and minus x here and simplify and get the formula as my dy by dx is going to be limit del x tends to 0, f of x plus delta x minus f of x divided by del x. So this is the formula for differentiation. This is called as the first principle of differentiation. Let's quickly have a look. So this is my increment in the function value. So again subtracting 1 from 2, we have this. And then from here we are trying to find the del y by subtracting. So this is our increment in y. So now to find the rate of change is called as the differentiation. What do we have to do? We have to divide del y by del x because we are dealing with the ratio. Del y by del x is equal to f of x plus del x minus f of x by del x. So this becomes the differentiation only when the del x is very, very small. So we are tending it to 0 and we arrive at this relation. This is a finite quantity as we have already seen in the table. It's a finite quantity, not necessarily 0, and the limit is called as the derivative of f of x with respect to x. That is derivative of y with respect to x. So how do we denote it? The derivative can be represented as dy by dx or f dash of x or y dash or y1. These are the ways that we represent the derivatives. The mathematical representation. And how do we read it? You can read it as d by dx of f of x or d by dx of y or f dash of x. Okay, so let's quickly summarize whatever we've learned so far. So the limiting process that is indicated by 5, this limiting process where we take the delta x tends to 0, meaning we mean to say that delta x is very, very, very small. This process is known as, it has a mathematical name, and that's known as differentiation, and it yields to a result. The result is called as the derivative. These are very, very important mathematical terms. So please pause the video here, take down these terms so that you're familiar with it. And the function whose derivative exists at that point, meaning when we differentiate a particular function, that function, if we are able to differentiate, then that's called as it is derivable. Since we are able to differentiate it, it's called as derivable at that particular point. We'll look into more examples. It may be verified that, now let's suppose a function is derivable at a point, then it means that the function has to be continuous. We've seen continuity and limits of a function in the previous chapter itself. You can go revisit it for better understanding. Only when a function is continuous, it can be derivable. Meaning, when you graph a relationship that is given to you, it should give you a continuous curve or a line or a particular shape. It has to be continuous. You shouldn't be taking out your pen for any reason when you graph it. Only such functions will be differentiable. And all continuous functions need not be differentiable. So what do we understand from this? All differentiable functions should be continuous, but not all continuous functions are differentiable. Now, these things we will definitely look into with examples in our future videos, but as of now, please understand the facts behind it. Okay. Now, this delta x might be a little uncomfortable for people to write, right? So now, you can substitute it with a normal delta, a small triangle, and say delta x for your ease. So the increment can be represented by this delta x instead of this. And the derivative again has different ways of representing it, which I have already explained it to you. Okay. So with this, we'll move on to applications. So we've learned something. We'll try to put it into application and see whether we are able to differentiate it. Okay. So find the velocity of particles moving along a straight line for the given time distance relations at the indicated values of time. Meaning, he's given you a relationship between the time and the distance. Your S is a function of t. And you are asked to find the velocity of the particle at t is equal to 5/2. So now what is velocity? It's a rate of change of your distance with respect to time. Your time is a variable quantity, your distance is a variable quantity, right? Because you cover distances as time goes. So is it always uniform distances? Not necessarily, because in everyday life, you have a lot of challenges. There could be traffic, there could be friction on the road. Of course, it's not manually possible for anybody to cover equal distances of time in equal intervals of time, equal distances, right? Not always. So now, unless and until it is a periodic motion, correct? So now, S is this. Now this is our relationship. We are going to find the velocity. As I said, velocity is nothing but change in distance with respect to time. That is ds by dt. So do we have a formula for this? Yes, we do have. We've already seen the formula. Let's have a quick recap of the formula. So the formula will be limit delta t tends to 0. Why do I take delta t? That's always my independent variable that should tend to 0, that is where I make changes that impacts my dependent variable, is equal limit delta t tends to 0, delta s by delta t, that is nothing but limit delta t tends to 0, f of t plus delta t minus f of t by delta t. This is your formula. Please make a note of this. From the previous slides itself, you would have made a note of it. So as and when the variables change, you need to know how to replace and where to replace which variable. Okay. So now let's have a look how we are going to solve this. So we have our s is equal to 7t square minus 4t plus 1. So there is a change in that is delta t, right? So let's add it. So this is my f of t plus delta t. This is my f of t. Let me first write that. F of t is equal to 7t square minus 4t plus 1. So what is my f of t plus delta t? So when I have t inside the bracket, I have t's everywhere on the right hand side. Now what do I have inside the bracket? I have t plus delta t. So in place of t, I should replace t plus delta t. That is it. It's as simple as it is. So instead of t, I'll write it as t plus delta t the whole square minus 4 into t plus delta t. There is no t in the last term, so I just keep it as a constant here. So this is my function translation. It's very, very simple. You'll be able to do it. So let me replace it here in the formula. So now it's quite difficult for me to continue here. I'll put this here and then I'll continue. I need the entire board. So let's put this function here. Limit delta t tends to 0. Our delta s by delta t is going to be limit delta t tends to 0. F of t plus delta t minus f of t by delta t. Okay, let me now erase this. This is our velocity that we are going to find out. Okay, now let's replace whatever we have. So this is going to be equal to limit delta t tends to 0, 7 t plus delta t the whole square minus 4 into t plus delta t plus 1. That is my f of t plus delta t. Then minus f of t is there. So let me replace my f of t now. Since it is after a negative, after a minus, I'm going to change the signs of every term that follows. I'm sure you all would know this. Divided by delta t. Now how do I evaluate this? I need to simplify it. How do I simplify? I'm able to see identities. Let me open it up, simplify, cancel out the like terms and all that and see what I get. Okay. So this is equal to limit delta t tends to 0. This is a plus b the whole square. So 7 into t square plus delta t square plus 2 into t into delta t minus 4t minus 4 delta t plus 1 minus 7t square plus 4t minus 1 divided by delta t. Now again I have something here. Let me simplify and see what do I get. So this is 7t square plus I'm multiplying this inside to simplify plus 7 delta t the whole square plus 2t delta t minus 4t minus 4 delta t plus 1 minus 7t square plus 4t minus 1 divided by delta t. There's a small mistake here. This should be, here this should be 7 into 2t, that is 14t delta t minus 4t. Okay. So let me simplify even further, look for opportunities. So 7t square minus 7t square gets cancelled out. 4t plus 4t gets cancelled out. So what do I get? 1 and minus 1 goes off. So I'm left with limit del t tending to 0. All the terms that are left out has delta t common there. You know, before we apply limits, it shouldn't be leading us to a 0 by 0 form that we've already seen in previous chapters. So first let's eliminate that because our denominator has delta t and that is tending to 0, which will not give us a finite value. So let's see what we can do. Now I'm taking delta t common outside. So I'm left with 7 delta t because 1 delta t is taken out. So it's 7 delta t. Let me place this here for convenience. Then plus this delta t is taken out. I have 14t. And here delta t is taken out. I'm just left with minus 4 and I have by delta t here. So this and this can be cancelled out now. So now let me apply the limits. It says delta t tending to 0. Meaning wherever I have delta t, I need to make it into 0. Because it's so small, that's almost 0. So for my convenience, I'm making it 0. So 7 delta t, since it's 7 into 0, it gets nullified. So I'm left with 14t minus 4. So this is my 14t minus 4. So this is my ds by dt. Have you all understood? So the derivative ds by dt, otherwise that's the velocity, is nothing but 14t minus 4. Please go through the video once again, go back, look into the process, solve it once, you will definitely understand. Well, so with this, we'll move on to the next question. Okay, so now we have found out our velocity, but the question says, we are supposed to find the velocity at the indicated values of time. So what is my indicated value? Exactly at 5 by 2 units. It could be seconds, minutes, anything, because the units are not mentioned here. So 5 by 2 units of time, we need to find the value of its velocity. So what is my velocity? I've got the velocity as ds by dt, that is equal to 14t minus 4. So I need to find the velocity at t is equal to 5 by 2. That is nothing but 14, replace the t by 5 by 2. So what do we do? It's again broad mass. First let's multiply. So 7 into 5, that's 35 minus 4. That is equal to 31 units of distance. So this is my solution. Hope you all understood. So we are supposed to find ds by dt, the rate of change of distance with respect to time. So we know the formula. It is limit delta t tending to 0, delta s by delta t. That is nothing but limit delta t tending to 0. F for, here it is not f, this is s. S of t plus delta t minus s of t divided by delta t. The function is named as s here. So this is s of t is what we have given here. We have been given here, that is distance in terms of time. So that is nothing but 10 minus t square plus t cube. Now what do we want? We want s of t plus delta t. So let's find s of t plus delta t. Wherever t is there, we are going to replace it by t plus delta t. So 10 minus t plus delta t the whole square plus t plus delta t the whole cube. Let me simplify it here only before I replace because it becomes easier. So let me find the value of this. This is 10 minus, this is a plus b the whole square. Let me put it in the brackets because there is a negative sign outside. So t plus delta t the whole square plus 2t delta t plus, this is the whole cube, a plus b the whole cube. That is nothing but a cube plus b cube plus 3a square b plus 3ab square. This is what we have. Let's open up the brackets and try to simplify it. Minus t square minus delta t the whole square minus 2t delta t plus t cube plus delta t the whole cube plus 3t square delta t plus 3t delta t the whole square. Now let's substitute it here. We have s of t plus delta t is here. 10 minus t square minus delta t the whole square minus 2t delta t plus t cube plus delta t the whole cube plus 3t square delta t plus 3t delta t square. Let me put a partition here. Minus delta t, minus s of t. S of t is here, minus 10. So since it's after minus, I'm changing the signs. Plus t square minus t cube divided by delta t. Now let's see how we can simplify this. This goes off, this goes off, this goes off. So I have only terms which has delta t as companion. Okay, so let me take delta t common outside. After this, let me solve it out here. So I'm going to take delta t outside. So limit delta t tending to 0. I have everywhere delta t. Let me take it outside as a common factor. So 1 delta t is out, so it's minus 2t. And here also 1 delta t is out, it's minus delta t. And then it's with this delta t is out, we have plus 3t square. And then delta t the whole cube, again the delta t is out, I have delta t the whole square. And then here delta t square, 1 is out, so I have plus 3t delta t divided by delta t. So again I can just cancel it out. Now I'm going to replace the limits. So delta t is 0. So wherever delta t is there, all that gets out to 0. So I'm just left with minus 2t plus 3t square. So what do I understand from this? My ds by dt is equal to minus 2t plus 3t square. Does my question end there? No. I'm supposed to find the speed at 3 seconds. Okay. So this is at the end of 3 seconds. Meaning when my time period is 3 seconds, I'll have to find my ds by dt. That is the speed, the instantaneous speed at the end of 3 seconds. So ds by dt when my time period was 3 seconds is equal to minus 2 into 3 plus 3 into 3 square. So I have minus 6 plus 27. That is 21. What is my unit here? Is the unit of distance given? Yes, it is meters. And the unit of time is seconds. So we are dealing with ds by dt. That is your speed. That is nothing but distance by time. And your unit is going to be meters per second. So our answer is 21 meters per second. So the entire solution is here. Just go through it. Pause the video and do it again. Go back and visit if you have any doubts. So we've learned this method now. It's a very, very long procedure. Don't you all think so? So if we have simpler formulas, generalized formulas, it will be much more easier to differentiate. Otherwise, it's a very long procedure, finding the change in everything and then tending 1 to 0, factorizing it, applying the limits. It's little complicated, right? So in our upcoming videos, we are going to see how quickly and easily we are going to differentiate. Trust me, it's not going to be this long. Thank you. Sai Ram.